Good morning, afternoon, evening, depending on where you're joining us from, everyone. Thank you for joining us today for the SEG Near Surface Technical Section Student Subcommittees our next entry in the open source software webinar series, where this month we are having the wonderful folks behind PyGIMLi come through and talk to us about its functionalities and get us through some different materials and references they have prepared for us. Before we begin, the model for this webinar is a short presentation they'll be guiding us through. If you have the link, and I'll throw this back into the chat here, there's a GitHub repository that they have prepared that you can download and follow along with. There is Joshua. And not sure for a question for the PyGIMLi folk if you have any preference on having a kind of like a dedicated Q&A session towards the end, or if you're planning just to answer questions as they come in.
I think via chat we can answer them on the fly, and maybe in discussion at the end would be good.
Sounds good. Yeah, so as any questions come in, feel free to drop them into the Q&A section, so that way they can be saved and quickly just kind of filtered out from the rest of the chat. So I will kind of stop talking for a bit, but I'll do a quick introduction of our three presenters. With us, we have Thomas Gunther, who's a geophysicist and senior researcher at the Leibniz Institute for Applied Geophysics in Hanover, Germany. We have Florian Wagner, who is a full professor in applied geophysics at RWTH Aachen University in Germany. And we have Carsten Rucker, who is a geophysicist and now a researcher at the Federal Office for the Safety of Nuclear Waste Management in Berlin. So more details about their backgrounds and their bios can be found at that link that was previously posted. And I will sit back and let y'all take over.
Chris, thanks a lot. It's a great pleasure to be here. 160 people already, so thank you all for joining. On behalf of the others, it's a great pleasure to welcome you to this tutorial. We would start with what PyGIMLi actually is, and today we would like to go a bit beyond the standards. So what can we do to really tweak our inversion and put in as much as prior information as we have available. Chris already introduced us, so there's no need to further do that. Carsten will serve as the back office today, so all the questions you have, post them in the chat, and he's happy to answer them on the fly. And then in the end, if we have time left, we are also happy to discuss a bit more in detail. So we think of PyGIMLi as a versatile toolbox. It holds many functionalities, for example, for the management of 2D and 3D meshes, both structured and unstructured. It holds solvers, finite element and finite volume solvers, which are computationally quite efficient. This is all the computationally heavy part, like the solvers and the mesh management, is implemented in C++, and everything is fully accessible via a Python wrapper. There are many geophysical forward operators that make use of these solver interface. We will mostly focus on the ERT data set today, but there's induced polarization, seismic refraction tomography, gravimetry and magnetics in 3 dimensions, electrokinetic streaming potentials, some EM compatibility. And these forward solvers can be used on all the different mesh types. You can plug in your parameterization and use them to create synthetic data or to combine them individually in inversion frameworks. And This could be a conventional mesh-based smoothness constraint inversion, but we also have the options to constrain things both spatially and in time, to do different types of joint inversion, and to also link geophysical data with process models for fully coupled process-based inversions. And one of the key features is the region-specific regularization, so that you have very flexible control on previously defined regions to incorporate prior knowledge, but also their behavior during the inversion. And we will also demonstrate a bit of that in the tutorial later. Of course, as the webinar series suggests, it's all open source, platform compatible, and documented and tested. And also, as part of the webinar series, it's well suited for teaching. We also use it a lot for teaching ourselves, and due to the fact that everything is transparent, open, and written in Python scripts, it's reproducible by default. Carsten Rücker actually wrote the first lines of the code in the late 90s, if I remember correctly, but it took quite some time until 1.0 was published, and this was in 2017 in Computers and Geosciences, and we were really happy how it was picked up by the community. Not focusing on the citations here, but what really makes us happy is that it has been used in over 100 peer-reviewed journal publications. So there are really, quite some fascinating studies already leveraging upon PyGIMLi. Three, let's say guidelines. We try to make the easy things easy, the hard things possible, but everything should be transparent and reproducible. And today we want to particularly focus on this second part. How can we do the hard things? So something that you cannot do in a graphical user interface, for example. So how can you really link things together and incorporate prior knowledge? This is not the first tutorial. If you search for PyGIMLi on YouTube, there are other tutorials, in particular the ones that we gave in the frame of the Transform conference organized by the Software Underground. And in 21, we focused on how to create geometries, how to mesh these geometries, how to populate these meshes with boundary conditions and subsurface parameters to solve partial differential equations on these meshes, and also demonstrated a conventional inversion, but also using a forward operator from a different software package. In 22, Thomas focused more on fundamental data or fundamental objects, in particular the data container and the mesh, some matrix types that we have implemented. And then he went over to regularization and also treatment of different regions. And this is also where we would like to make the link today. So you do not need these tutorials before, but for those of you who have seen these tutorials, I think there will be a lot of new things today. And particularly we want to focus on a real life 3D data set that Thomas will introduce later, and then start with a simple inversion and increase in complexity and really tweak things beyond the standard practice. So this is today's rationale. Also, since these last tutorials, 21, 22, a lot has happened, and just a quick overview. So all the notebooks that we made available with these tutorials are also on the website now, integrated in our tutorials and examples sections. We have improved on the 3D visualization, leveraging upon PyVista, also with interactive notebook compatibility. There's 3D gravity and full tensor magnetics, also with corresponding managers that you can use within the inversion. Some new matrix types, more efficient Jacobian calculation, for example, and an LSQR inversion framework that might also become the default inversion framework at some point. Right now it lives in parallel, but it particularly enables additional parameter relations. So In the conventional inversion, Gauss-Newton-based inversion framework, you were able to constrain the parameters, but you were not able to constrain, let's say, relations between these parameters. So if you are inverting for the thicknesses of two layers, with this new framework, you can also constrain the sum of both thicknesses, for example. And we used this in this paper here to estimate liquid water and ice content, and to also make sure that these four fractions sum up to 1 in the end. There's a new multi-frame modeling that Thomas contributed, and the most common use case would probably be time-lapse inversion that we will also demonstrate today. But the frame cannot only be formulated in terms of time, so it could also be different frequencies in terms of a spectrally constrained inversion, or you can also think of different one-dimensional soundings stacked next to each other, so laterally constrained inversion, for example. So this is why we came up with this more generic term, multi-frame modeling. The time-lapse ERT class builds up on that, and will also be demonstrated today. And there are several new examples on the website. So yeah, make sure to have a look around. And the website generally improved. So a lot of the things that were formulated in the old style are now using the more modern frameworks that we introduced with PyGIMLi 1.2. And we also moved to the widely used PyData Sphinx theme, which you also see in one of the in the popular packages like NumPy and Matplotlib. So this makes it much more responsive, and hopefully also a bit more structured to navigate through. And finally, there are a lot of new convenience functions to make your life easier. Also, of course, since the last tutorials, a lot of papers based on PyGIMLi have been published, and we also have this list here on the website, which is actually hard to keep up to date. So make sure to have a look, and if you have used PyGIMLi in your research, we would very much appreciate if you could add yourself to that list. This also is along the lines of this community call, if you want. So we would really like to gain new users, but also contributors, and contributing can be on many different levels. So you do not have to be a professional Python programmer to contribute. You can also go through the documentation and tell us what could be improved, or you could just fix some typos on the fly. You can start by joining our channel on Mattermost. So this is the Mattermost instance of the software underground, which was recently moved from Slack to Mattermost. So make sure to join the PyGIMLi channel. Today you can also ask your questions, of course, here in this Teams webinar channel. But to keep the discussion going afterwards, this would be a good address. We are also, of course, on GitHub. So if you want to start a discussion there on potential new features, or if you find an issue in the code, that's a good place to do so. And you can also contribute to the website. So I can quickly demonstrate this. I have the website open here. So if you go through the examples, again, there are many new examples also in 3 dimensions, and also the 3D scenes are now interactive. You can do these kind of things. And if you think that something could be improved, you can use the Improve This Page button to the right, and then can actually edit the code to reformulate a sentence. So, like, the contributions can be very small, but every small contribution is highly appreciated. And also the database with all the publications can be added, so you can add yourself to this list. And we also welcome any examples, so you can either send them by mail or contribute them directly to the code. So this would be, let's say, the highest level of contribution if you really add new functionality or modify functionality. We have outlined the ways to do so in the contribution guidelines. So this would be here, contribute to the code. It's basically a conventional workflow on GitHub with a few PyGIMLi particularities. But yeah, that would be a good place to start. And again, this was the publication list that I mentioned earlier, where you can also search for, let's say, some keywords, joint inversion, and then you can find actually real-life publications that use PyGIMLi for joint inversion. Okay. So this, yeah, kind of the intro. A few things on how to follow along. So we will start with an empty notebook today and really program step by step. If you want to follow, you can do so. The only thing you need is essentially PyGIMLi 1.5.0 and a Jupyter Notebook. If you have PyGIMLi installed, then you can also update it. If you start from scratch, then the webinar repository that Thomas will also show later would be a good starting point, and you can download or clone it. And if you are in the folder, you can type conda env create, and this will install everything you need. And after activating this environment, you can start the Jupyter Notebook, and you should be able to type import PyGIMLi as PG. If you do not want to go through this installation, you can also follow along using Google Colab, for example. So there's a new pip installer, which makes usage of PyGIMLi on Colab quite handy. So you would just need to type this line into an empty notebook. And with that, I like to hand over to Thomas.
Thanks, Florian, for the invitation. I'm going to share my screen. So we're starting off with a story. And the story will be about, just a moment. The story will be about a time-lapse ELT data. Can you see my screen? Yes. Okay. So,
yep.
With the time-lapse ELT data, so we created a single story of one long notebook together, starting from scratch, which is about 3D time-lapse ELT data. We will load and process and visualize our data, do inversion and work on different types of meshes, and use different types of regularization approaches and strategies to include any type of additional information you might have, like prior information. We will also try to bring the petrophysics into this workflow, visualize our results in 2D, but also in 3D, also doing 3D inversion. And eventually we will finish up by doing some time-lapse inversion. And of course, this notebook is not perfectly suited for all these strategies that we will discuss, but we will provide a lot of references to it. So if you go to our GitHub repository in sec24.pygimli.org, you're ending up in our GitHub repository where the local where the installation instructions are also done. You can do so in Google Colab, but you get some references. But what you also got is the slides that can be viewed here on this link, on the GitHub IO link. You can see the slides that Florian just showed. And but we will mainly follow everything in one ready prepared notebook, which is called Index iTyping Notebook. And there's everything in from the very start to the very end. We have a lot of text. So starting from our property, explaining things and background, and most importantly, there are a lot of links to examples and tutorials and notebooks that we've created, which are really good, meaningful examples for the strategies we are going to talk about it. So you can follow everything here. You can read here. You can click the links for full details. But I will now start off with an empty or an almost empty notebook. I created a notebook in Jupyter Notebook. I hope you have all seen this, and I'd like to start off explaining a little bit on our task we are doing. So this paper was published by Hübner et al. in Hydrology and Earth System Sciences in 2017, and it describes an infiltration experiment which has been followed by 3D ELT. So we dropped a lot of electrodes there, almost 400 electrodes on the ground, and we were interested in how the infiltration into this blue into the blue rectangles, we're going into the subsurface through the individual layers. So you see a top view of the electrodes and everything here. And we want to work on these data. So we all like to work on these data, but a few things we need. Before I typed it already here, so we need some basic libraries to import. Most of you will probably be aware of a NumPy library, which is providing the basic algebra. Also, matplotlib is really good for when it comes to 2D plots. Then we of course use PyGIMLi, which we import by import PyGIMLi, and as we are lazy, we are just writing PG instead of PyGIMLi to make codes shorter. But we're also gonna import 3 different modules of PyGIMLi. So in the physics, there's a lot of different stuff like travel time and gravity magnetics. We are going to work exclusively with ERT, but most of the things we will be talking about today is also transferable to any type of physical investigation like magnetics or whatever. Then we will work with mesh tools, and finally we are using an interface to PyVista, which is a really powerful 3D tool. Okay. I'm going to present everything in the side-by-side screen, which is putting everything on the right-hand side. So I'm calling these Jupyter Notebook cells, and I'm moving through. Actually, I'm starting with number 10, and I'm starting with reading in the data. Instead of downloading the data from some repository, we have some repository that recites all the different data files used in the tutorials and examples. And this is an example data set. The link is also in the webinar GitHub repository. And we have a bunch of different data and models and additional information. And if you go to the ERT, you will see a bunch of crosshole, bedrock detection or whatever. And we are making use of some data sets. I've just selected a few of those data sets for the time-lapse inversion. Actually, we have almost 200 time steps. So every data file is here. And to load it, we don't have to download it. We can make use of a PyGIMLi function, get example data. So you can type PG, get example file, and then you can shift tab. You can look at the doc string of this function to see what you can use it for, and there's even a shortcut to it, which is just telling from where exactly in this example data you are using it. So we will go to ERT, we will go to Hypno 2007, and then we will use one of the data sets, and I'm just choosing number 07007.dat, and we are reading it. And on the right-hand side, you see the result of this. And you see it's going to look in GIMLi org example data in this repository, and it returns something which is called a data container, which is having almost 400 electrodes or 392 electrodes. Data containers can also hold different types of information, can hold travel times, can hold magnetic data, whatever. It's a very general procedure. There's more about in the Transform 22 tutorial. And we have actually 2,849 data, and every one of the data has several columns in a sort of a dictionary. So we have an A and B column for the current injection, and we have an M and N column for the potential measurements. So those are just numbers pointing into the sensors. And we also have a resistance. So actually, we want to work with this. So that's why we write data before it, and then we can type data, and here we go. So we have this data object. Actually, we can retrieve a lot of information from the data. And so there's, for instance, data sensors. These are our electrodes, and you see this is a long vector of electrodes. Actually, we were interested in the X values of our electrodes to have a look at this, and then we see this is a list of 392 values. So we would like to plot them. So we use the plotting toolbox plot, and we use the X values of the data and the Y values of the data, and plot every electrode by an X or something like this. And here we go, and then we end up in in a figure like this, which is displaying our electrode distances. So we have 14 lines in the y direction. We have 14 lines of 18 electrodes, which is spreading an area of 5.5 meters by 2.6 meters. And this is what we're investigating in now. So actually, we just seen we have we should print the data again. And we see the print here. We have resistances. Actually, we are interested in the apparent resistivities. So what we're going to do is we need some geometric factors. And for this we're using the ERT module. And we are looking at the ERT module. So if you just target ERT dot, then there's a lot of functions in this ERT module which are specific for ERT. And there's, for instance, a function geometric factors, which you can just pass the data, and then you see this is a vector of 2,849. We know this number, and we have the geometric factor. So we can store this in the data. So we can put this into a field called K as probably a German name, and then we can have a look at the data. And now we see we have not only A, B, M, and R, we also have a field called K, and we can put whatever fields in we like to. So we can name them as we want to. But actually, we want to multiply the geometric factor by the resistance, and that's what we do. Data K times data R. This is producing a long vector, and this is going to be filled in the apparent resistivity, which has some historical name, which is rho A, which is apparent resistivity. And if you look at this, then we see also rho A. There's also a valid mark where we can temporarily exclude data files without removing them from the data. And then we have a data set which should be good for inversion. Actually, when it comes to inversion, we will need also an error. And I will quickly also do this at the very beginning, because there's not too much time to talk about error analysis. But in the full paper, there's a link into a procedure called normal reciprocity error, and there's an example on the PyGIMLi webpage where you can read all this on a published paper. And I was just saying you can not only fill in a vector into. I was just saying I have good data, and all data the voltage gain is not really playing a role. So I'm just feeding them with 2% of the errors, and here we go. And we don't talk about errors again for now. But of course, we can discuss it later. So now we would like to look at the data. So we can do something like data pro and see a lot of things that we can define on looking at our data. And as this is 3D data, which is actually on all the X lines and all the Y lines, a dipole-dipole array, but also some sort of a multi-gradient array. So we're injecting the currents at the outer electrodes and measuring in the middle, using an equatorial dipole-dipole, so which is injecting the currents in the dipole and measuring parallel to it on the next line and the next line. So actually, we cannot easily show this as a pseudo section, because we would have to extract the profiles. But what we can do is to make a cross plot over A and M. This is just a style called A and M. And if you do so, we see a cross plot, which is just a rough estimation of our data, which is not really nice. But we see something that looks like a pseudo section, and we will go into that in detail. So we have on the main diagonal here, we have pseudo sections of inline profiles. But then we also see some mirror pseudo section on the other axis. So on the y-axis, there's the number of A electrode, and on the m-axis, there's the potential electrode, and the B and N electrodes are just next to it. So we don't need it right now. So these are the inline profiles. But then we also have equatorial dipoles, which are measuring between the individual lines. And this is how we end up here. But to work on 3D data is really a bit complicating, which is why we are going to extract a profile from it. And for extracting a profile, there's a nice function which is called subset. You can call subset for whatever. You can type something like I equals 10, and you would extract all data with a 10 amp current. In this case, we will use an X value of 1, and this is producing a pseudo section. Now, this is producing a data set which is having only 14 electrodes. We remember there's 14 axes if you count them, 14 axes on one X value. So we're extracting all data gathered along this line. And then we do so. And they are having the same features. Actually, they are also having an XM and XA and XB, which is a result of this extraction. So if we call this X1, then we can work with X1. If you now look at the sensors, which are the electrodes positions, then we have the X position of 1 for every electrode, and the Y position, which is increasing from 0 to 2.6. But actually, for 2D inversion, this Y position should be the X position. So what we are going to do is to extract the Y position from the data, and then do it again and multiply it by 0. Then we're using the nice function numpy column stack. And then we have this numpy column stack is producing a stack like this. And we can use this. So we call this ePath like electrode positions. And then we just say set sensors ePath. And if we then look at our sensors, then we also have a Y position. So it assumes that the set coordinate is also 0. And then we have a data file, which is really like a 2D data set, which we can work with. So and then we can actually also visualize this data. And for this reason, we can only work with x1.show, which is presenting a pseudo section, because now we have 2D data, which can be much easier be explained. And we see a dipole-dipole pseudo section of different dipole-dipole levels increasing. And so every block is one data set. Every data set has the same area of representation. And you see already in all show functions, you have two return arguments, which is one time an axis, and the second is a color bar. So we can write something like x of x and cb to it, and then we can do whatever we want with these axis objects. I ask some data, and you can do it, and then you see the title. So we can customize our axis, our aspect ratio, whatever we want to do, because this is all matplotlib. This is really easy. So what we want to do now is to work with these data. So first we might do some processing. Actually, you can say, well, this is a very low value. So actually we are in a rather dry background of really coarse material in a forest, in a forested area. And you might say, well, I don't like values below 250 ohms. And that's why you can filter this data, and you can just say remove x1 apparent resistivity is smaller than 250, and then you x1.show. And then you see the filtered pseudo section, which is almost the same, except that this one position is missing now. So maybe that's a better data set, but if you write it down like this is some sort of a protocol, so we can use very complicated logical operations to work on the data and really explain what you do with the raw data until the final figure. And this is one of the most important features in PyGIMLi. And well, of course, we want to do it in version mode with this data. That's why we are creating an ERT manager. So that's for every physics, there's a manager which we can actually already pass the data. We just call it MGR, like manager, and well, actually not doing much. But what the manager can do is to do an inversion. Sorry, kernel seems to be died. Okay. So seems that somehow our kernel died. Then we just restart the whole notebook, and we will hopefully be there in an instant. So really strange mistake. And this inversion puts out some additional information that can be used as a protocol or whatever. And this is returning some wave. Well, actually, I would be interested in what happens with my data. That's why I'm adding verbose equals true, and it's putting some more information, and it's starting with a chi-square of 400 and something. down to almost 1. So I'm almost fitting my data, which is kind of nice. So first I want to look at how I'm fitting my data. So that's why I'm using this manager to show the fitness of the data, which is the comparison between data and forward modeling response. On the left-hand side, you have the figure that you already know. On the right-hand side, you have the forward modeling response. So this data point is missing, and from a visual point of view, you can hardly make a distinction between those two. And there's an RMS value of 2.8% and a chi-square value, which is really nice. So this looks really good. But you might look into some more detail, and then you can call the show misfit function, which is representing your relative misfit of your data, in this case in percent, or also weighted on the error level. And you see there might be some systematics in the data, but otherwise the data are plus minus a few percent and a kind of Gaussian. So you might be happy with this, and then you might be entitled to look at your model, because if a model cannot fit the data, then you should not really try to look at the model. But now we can look at the model. And this one we can just do with show result. So again, we have two return arguments, which is an axis and a color bar, which we can later out. And then we see some subsurface model. Okay, this is generating a subsurface model. Actually, we'd like to look at our model with the same eye in the future. So using always the same color scale. That's why I'm creating here some sort of a color scale, which is a dictionary of of course minimum values of a color scale. Sorry, C min equals. So I might go to rather high value of 500 meters, because we will see also much higher values, and a C max value of 3000. And then you can work with, if you put this in, then sorry, star. So this is unpacking the dictionary. So this is like writing this into here, but I can use this star keyword argument again and again. So I can, of course, use whatever color map I like. If you're a fan of plasma, then use plasma. And then I like to add a few more things. Usually you're working in the logarithmic scale, and you see this is already logarithmic scale, but of course you can turn it off. I'm just writing it here, and I just don't like to discuss too much on the coverage value, which is blending out this poorly covered cells, and that's why I'm going to use this. So actually, I'm just going back to the kind of normal way, normal color map, which is a spectral color map, blue at conductive and red at resistive. Okay, so now we have a result. We will now go into more detail on how to play with these variables. People might ask, well, I don't like those triangles too much. I rather like rectangles. Of course, you can do so. So then you just have to define some grid. So the easiest thing to do is to create a grid, like starting from minus 0.3 to 3 meters and at a 10 centimeter spacing. And if you then do the same for the y-axis, which is the negative axis, and you start at 1 meter, and you want to end up at 0, then you type something more than 0. Then you just create a grid, which is just so you are using the mesh tools. Create grid. This is creating a grid. You see already this is a new object type. This is a mesh with 363 nodes and 320 cells. So we are just calling this grid, and we are just showing this grid here. So this is how our grid is looking like, and actually what we need to do is to add some boundaries to the model, which is saying that the upper boundary of our world is a normal no-flow boundary condition, and the other boundaries are mixed boundary conditions in the middle. And I can markers boundary. What boundary marker is. And then you see this is our mesh. And if you want to see the mesh additionally, then you just tap fill mesh equals true. And this is our mesh with some boundary conditions which is a -1 at the top and which is a -2 at the end. Okay, we want to use this mesh for the inversion. So basically what we do is to tell the manager, well, you should use the grid for the inversion. Then we again do the invert. And then we call again go result with the same keyword arguments. And here we go. Again, it's doing some inversion. It's presenting something, and to avoid all this stuff, I will now, just to make it easier for you to follow, is to get rid of this is using a PyGIMLi logger, and I'm just setting the log level to 0, which is deactivating unnecessary information. So actually, this is somehow written. That's why I'm writing robos equals false, and then we see only the mesh that we're interested in. And this is the result of a regular mesh, which has a similar, of course, similar subsurface resistivity distribution. Okay. So now we have some result, but actually we might say, well, I'm not too happy with a result. I might talk. I might go into more details. And we do this with a profile in a perpendicular direction, because later on we were going to do a 3D visualization. For now, we are just saving the result. So I'm just calling, I'm just using the inversion mesh, which is called power domain, and I'm just calling it x1 result is power domain. So this is just saving the mesh, and I'm now populating it with just like the data container. I can populate any feature with it, and I'm just putting in the model with it. And now we see that it has the same nodes and cells and boundaries, but it additionally contains one data set with resistivity, and it could with conductivity and coverage and resolution analysis or whatever in. So that you have one object to show later on. Okay, now we're going to switch to a perpendicular profile. Again, we do the same thing. You use a subset of a y direction. So data subset y equals 0.6, and then we see it. And if you look at the sensors, then we see the x positions are already correct, but the y positions are not really right. That's why I want to multiply it by a NumPy array, which is 1, 0, 0. So I'm multiplying y and z directed by 0. If I'm doing so, I'm canceling out the y positions, and I can now set these positions to the y sensor positions. And then I can show the pseudo section, which is in this case only a multi-gradient data with this, which is shown as a Schlumberger type of data set, and we have also apparent resistivities between 500 and 2000 ohms, just as we had before. Okay, now we also go into inversion, and we also create a new manager, just using the same one, but I don't need it anymore. So I'm creating a new manager. I'm putting in my data, which is called y1, and again I can do some inversion, and again her result using the same keyword arguments, and here we go. And then we have a model which is looking a bit different. So in the X profile, we see the infiltration zone that we crossed from here to here, almost on the whole profile, whereas on the Y profile, which runs downhill, it is only present in the well, let's say from 30 to, or from 20 to 30 of the data. Okay, that's why we just see the infiltration zone only here. But later on, we will bring together the X and Y information. But actually, you might say, well, I don't like this grid. This is really too coarse. I don't like it too much. And that's why I'm creating a geometry here. So I'm again using the mesh tools, and I'm using there's a lot of great functions. You can create circles, cubes, cylinders, faces, grids, whatever. There's really a lot of things for playing around, for defining your geometries. What I'm using is a great power mesh PSC. So PSC is a piecewise linear complex, which is not yet a mesh, but it's an input for a mesh. And we will say create something useful from the PSC and show the PSC. So then we see here some sort of a mesh with two regions. The one region is outside, and this is usually used for boundary conditions. And to see a bit more, I will just set the outer boundary to be a little smaller and to make it just better visible. So we have some outer space which is just used for the forward calculation, but inside the inversion domain is the yellow domain, and this is having a different region marker. So I can now specify a lot of things in this column. To see that, for instance, I can specify on how deep my model should go. So I can say, well, I'm not interested in anything deeper than 1 meter or 3 meters. Then you see it instantly. You can also talk about refinement, but to see the refinement, we should create a mesh first, and that's why we are using the function create mesh, and use the PSC, create a mesh, and call it mesh. And of course, we want to create a mesh, and this is creating the mesh. Again, we like to look at the markers, and we like to look at the mesh itself. So we say show both, and then we see the mesh here, which is still a really coarse mesh. Actually, we can define the refinement and the edit trace by a parameter called RYBX. And I'm saying I want to have like 0.2. I want to have 5 segments between each of the electrode pairs. Then it's going to be a much finer mesh. But I can only have it if I'm having a significant data quality, and that's why I'm using a triangle. The triangle institute is a grid generator that is being used. I'm going to decrease the boundary a little bit more, and then I'm presenting a much better inversion mesh. And I also can say something like, I want to have smaller cells like max. I just want to say I don't want to have cell sizes above 0.05 square meters. And this is creating a nicer mesh, and there's always some way to improve it. So this way I can really work on my data on my mesh refinement. Okay, then we are happy with the mesh, and we are trying to look at the mesh. So we again say set mesh. It's becoming boring. So what's going on? Oh. Again, doing inversion, and then we see well, we have a little bit better representation of our subsurface parameters, but now this is the point where it becomes interesting, because we can really work on the inversion. But what we can do is to set regularization parameters. And there's a lot of parameters that we can look at. We can define it for every region, but we can also define it for some region, for some parts of a model. And that's what we're going to do later. We can define a starting model. We can define limits, upper and lower limits with different kinds of function, different types of constraints, first order smoothness, second order smoothness. So I'm just trying to play a little bit and say, I want to have a look at how this is looking the second order smoothness constraint. I'm using some sort of a Laplacian operator for the for the model. And then the model looks a bit different, but not too much, but still a smoothness. But one thing that is particularly interesting is to use geostatistical operators. And for this, you're not just having smoothness across the boundaries. You're defining correlation lengths with saying how your model says are cooperating with each other, and rather expecting something like a correlation length of 1 meter in the x direction and 0.2 in the y direction. As I'm doing so, you're ending up in a quite different model, because I'm saying, well, I'm expecting more lateral subsurface images. And so I guess this is the point where Florian should take over again, right?
Yes, thank you, Thomas. Happy to do so. So we have seen how to load the data, how to filter the data, how to invert it on both structured and unstructured meshes, and how we can tweak these meshes. And now we want to look a bit more in detail how we can incorporate additional information. And one type of additional information would be some structural information that comes from a different data set, let's say from a geological cross-section or from conventional interpretation of seismic reflection data, or in this near surface context, more likely a GPR data set. And we have seen the PLC, the piecewise linear complex. You can think of it just as a geometric definition that Thomas already introduced. So just to start there again, I'm showing the PLC here. PG show, not shop, of course. So this is the geometry that we've seen earlier. And now we want to add something to this geometry. And a structural horizon could be incorporated in terms of a line. So we can use the mesh tools package, which has a lot of methods that start with create, and to create different geometrical entities. And here we are looking at the line. You can open the bracket, and then in the Jupyter Notebook, you can press Shift-Tab to see, to have a glance at the parameters again and the docstring here. So this only takes 2 required arguments, a start and an endpoint. So as a start point, I'm saying here something like 60 centimeters, and depth is negative, so 10 centimeters depth. We saw a relatively near surface infiltration front. And as an end argument, I'm specifying a second point at, let's say, 3.5 meters in X direction, and I'm using the same depth here of 10 centimeters, so this is a flat line. And I can also show this line, but there's not much to see, it's just a line, right? It's more interesting if I add it to the already existing geometry. So I can simply add geometries together. This also works in 3D. So we have our PLC, and now this flat line that we incorporated. And again, here it's a flat line, but that could also be a dipping horizon, or it could have many points. You can a very versatile function is the create polygon function, where you can just provide a list of points to provide an arbitrary interface in the subsurface. Okay, but again, this is just a geometrical definition, and I want a new mesh, so I'm calling the create mesh function you saw before on this addition of PLC plus the line, and Thomas already introduced the quality criterion. So I'm setting a quality of 34 here, and I'm looking again at the resulting mesh. So now this horizon has been incorporated in the meshing. So the triangle edges a line along this boundary. Okay, so this was my geometric definition, and now I add this to the inversion. So I'm initiating the ERT manager here with the Y cross-section of this 3D data set, and then I set this new mesh that I just defined. And then I just call invert. And after the inversion, I want to show the result with the same keyword arguments. So this would be the call. And now we see that the structural horizon that we predefined is accounted for in the inversion. So I can also zoom in here, and you see that there's a very strong parameter contrast across this predefined boundary, and then it converts back to smoothing outside of this boundary. So what happens here internally is that in the first order roughness operator that is used for the smoothness constraint, the boundaries corresponding to this line are basically taken away, so they are set to 0. And although it's called a constrained inversion, we actually take away constraint from the inversion. So the inversion has more freedom in fitting the data. So usually adding structural constraints also leads to a better data fit. We can also check again the data fit. Thomas has shown this already, the chi-square error. So this is below 1 even. So the inversion now has more flexibility in describing the data. Okay, so this was just a horizon in the subsurface, and smoothing is disabled across this predefined boundary. But now we want to do a bit more. So region-specific regularization. So rather than creating a line, I'm now creating a rectangle. This has very similar arguments, so we also can define a start and an end, but then it creates a rectangle between these 2 points rather than a straight line. So here I'm going a bit deeper, 30 centimeters. All the way to the surface. And then I'm taking the PLC again that I had earlier, and I'm adding this rectangle to it. And then I'm calling PG show on this addition. Here we see the markers, region 1, this is the background, this is my actual inversion region, marker 2. And here I want to specify a new marker, let's say marker 3. And now I have 3 different markers, and I can set the inversion settings for these different regions. But again, this is just a rectangle, and I again need a mesh, so I'm calling the create mesh function again on this. So something like this. And then I'm looking at the resulting mesh. That looks good. And now to the inversion. So I'm going below here and setting this mesh again to the manager. And then I'm calling the invert function and looking at the result again. Okay, so this looks very similar to before. I've just added a new region. I've not specified anything else. The region comes with boundaries, and these boundaries are by default are decoupled from the surrounding region. So now we have this lateral boundary and also this boundary here at the sides. But now we want to do a bit more. So we have this region number 3. And we want to set some things to it. So I can, Thomas already introduced the regularization, set regularization, and now we can specify the region. So I say region 1 should be my background. This is also the default. Region 2 should have normal, let's say, second order smoothing. And now my third region, which is again this shallow, this is this area here, right, at the infiltration front. So we saw in the unconstrained inversion that we have like 10 or 20 centimeters of infiltration here. And now this box goes down to 30 centimeters. And in this third box, region 3, I can specify any other type of regularization, let's say a first order smoothing here. And I can also weight lateral versus vertical smoothness. So a Z weight of 1 would be isotropic smoothing. This would be the default. And if I set this to 0.3, then the smoothing in the vertical direction is only 30% of the global smoothness constraint. And I'm just copying this here. This is just a repetition inversion and showing the result. So that again looks very similar. We still have the structural decoupling, but now we can also set constraints acting between regions. And these are the so-called interregion constraints. And they are a bit hidden in the forward operator. The forward operator comes with the region manager. And this region manager allows to set interregion constraints. Interregion constraint. So now I'm defining a constraint between region 2 and 3. And I want to have this fully coupled again, so no decoupling. So I set this to 1. I redo the inversion. And now you see that the work. Yes, 2, 3. Yeah, let me quickly reinitiate the manager here. Okay, so now you see basically a smooth result again across this boundary, but you see that this infiltration front is much more pronounced in the lateral direction. So there's more smoothing in the lateral direction. If I set the Z weight to 1, then it looks very much as we had it in the beginning. So conventional smoothness constraint inversion. And by specifying a more layered regularization, but only in this region 3, I can make this infiltration front much sharper. Okay, this is nice, but when I'm looking at infiltrating water or CO2 in a reservoir, I might be more interested in actual saturations rather than changes in resistivity, for example. So we can also link our time-lapse geophysical data to petrophysical parameters and state variables. And for that, we have the Petro package. This is in PyGIMLi physics.petro. And here, something to relate electrical resistivities to water saturation. This is the well-known Archie equation, and we have it formulated in terms of porosity, or here we use the one defined in terms of saturation. So we import this, what we call a transformation. We can transform both in parameter and data space. This is a model parameter transformation. And here I'm calling this function. So I'm setting up a new transformation. And I'm calling this function. Let's have a look at the parameters. So it depends. So Archie's law, just as a recap, most of you will be familiar with it, but it basically states that electrolytic conduction dominates the process. So our bulk electrical resistivity will be mainly dependent on the resistivity of the pore filling fluid. So we have to specify the resistivity of this pore filling fluid. And this is here from the paper. This is 66 ohm meters with a temperature correction from 20 degrees. And then we specify a porosity of 40%, cementation exponent of 1.3, which is a pretty standard textbook value, and then a saturation exponent of 1.83. Of course, these parameters or the petrophysical model in general should be calibrated in terms of laboratory measurements in the ideal case. Here, I would just want to show the method. Okay, so now we have this transformation function. And what does it do? So it tells me that like a saturation of 0.5, so 50% transformation saturation leads to a bulk resistivity of 460 ohm meters. And I can also go the other way around. It also comes with an inverse formulation. So 463 ohm meters will result in 50% saturation. So it's a bi-directional transformation, and these two directions are also necessary for the petrophysical inversion that we are now attempting. Here I would just paste some plotting commands. So as we are looking at saturation, I'm just plotting values between 0 and 50% here. We don't do logarithmic scale, so this is false. I'm using a different color map here and a different label. So these are just keyword arguments for visualization. So I can now show the result from the conventional inversion that we had earlier. But rather than showing the model, I'm now applying this petrophysical transformation to the conventional inversion result with my keywords. And now I have a tomogram in terms of saturation, right? So 0 saturation to 50% water saturation. We see the infiltration frontier at the top. So this is just a petrophysical transformation of the image after a conventional inversion. But these petrophysical transformations allow us to also formulate actually a petrophysical inversion. And this is what we want to do here. So I'm actually in incorporation of petrophysics. So I'm reinitiating the manager. And what comes into play now is a new forward operator. So I have to define a petrophysical forward operator, which gives me the electrical system response due to a change in saturation. And for that, we have in frameworks, we have the so-called petromodeling, and this takes a conventional forward operator, conventional from a conventional geophysical method, here the ERT method, together with the petrophysical transformation. And this is Archie's law now, but this could also be something more complex, more sophisticated for a given lithology. Okay, and we have created a lot of different meshes. So let me just recreate a simple mesh without any structural boundaries or so to really just focus on the petrophysics here. So I'm just using the PLC quality of or. And I have to set this mesh again. And this is just the modeling. And now I need an inversion. And I can take the standard PG inversion. And this inversion is initialized with a forward operator. And I initialize it now here with my petrophysical forward operator. Okay. And now I should have everything in place already. So I can calculate a model using the run method of this inversion. I'm specifying a data set. Here, apparent resistivity of this slice. Also need to specify the error. Okay, what else do I need? Maybe a starting model. Remember now the inversion is formulated in terms of saturation. So my starting model is not in terms of resistivities, but in terms of saturation. So I'm specifying 20% saturation here. Then I'm showing the model something like this. Okay, so this looks very similar to the result before, but we have not transformed a conventional inversion result into saturation, but we have reformulated the whole inversion in terms of saturation. And this has a lot of benefits. And most importantly, we can now add prior information in terms of saturation. Right, so it might be the case that we have soil moisture sensors or TDR probes or whatever to have a handle on water saturation, or we know that we have some, I don't know, dry zones where we can assume zero saturation or close to zero saturation. So prior knowledge in terms of water distribution or in terms of the petrophysics can now be incorporated into the inversion directly. And this is what we have done here. And now we will see how this can be used in terms of a petrophysical joint inversion. So let's say I have soil moisture sensors in different locations at depth. So I'm just defining some here. Let's say I have these at different X positions. A and at different Y positions. So let's say at 10 centimeters depth. For all the X positions I've defined earlier. And at 50 centimeters depth, also for all the X positions. And of course, this does not work. So let me just enter. This is just a geometric definition. So let me just speed this up here. Okay, so now I'm having these positions. This is just a two-dimensional array, X and Y values. And I'm having saturation values at these points, 8 different values. Okay, so this could be TDR probes in the subsurface, for example. And now I want to use them as prior information. I'm creating an inversion mesh. This is just the parameter domain from my previous inversion. All the parameters were numbered in this parameter domain, so I'm resetting them to 0 here. And now I need a forward operator for my point information. And this I call the point forward operator. And for that, we have a framework. There's a framework for everything. Prior modeling. So any prior information you have can be used in this prior modeling on the mesh at the specified positions. Okay, so far so good. So that's yeah, a bit more typing here, but that's also, I think, a very advanced feature already, right? How you can integrate petrophysical inversion into petrophysical information in geophysical inversion. Okay, so now I have two forward operators. I have my ERT forward operator. I have my point forward operator. And I can do joint inversion in PyGIMLi by creating a joint forward operator. So this is always the first step to joint inversion. You need something where you can put a larger model in and you get maybe 2 or 3 model responses out of that. And we have this generic framework called joint modeling. And that is basically a stacking of other forward operators. So I have my forward operator from the ERT problem and my forward operator from the PyGIMLi problem. And this is the from the prior point data. I have to specify the data. Okay, so far so good. And now I need an inversion. And I can do a joint inversion by simply using the conventional geophysical PyGIMLi inversion class, but initialized with a joint modeling operator. Now I can set some regularization. Remember now the whole thing is formulated still in terms of saturation. So I can say I want physically reasonable parameter limits from 0 to 100% saturation. And then I just need to stack the data together. We have the PG_cut function for that. You can also do it with NumPy related functions. So this just holds the data values, so the apparent resistivities and the saturation at my point probes. Okay, so what do I have? I have an inversion mesh. I have a joint forward operator consisting of the ERT and the point prior modeling operator. I have an inversion setup initialized with this forward operator, specified with the physically reasonable limits. I have the data stacked together. So I have everything that I need. I can, of course, also set some smoothing here, let's say second order regularization. And now I can do the actual inversion. So I have a joint inversion result that I get from my joint inversion operator. I call the run function with my stacked data vector. I have to set some relative error. Let's just put this to 20% here, or maybe 2%. And lambda and a start model again. Okay. So now I will just paste the plotting code here and fingers crossed that everything works. Of course, I have to show the result as well. Oh, sorry. Okay. So I'm showing the result here. This returns a matplotlib axis, and then I'm adding the point information on the same matplotlib axis. Okay, so the whole thing converges, and we see the point information also color coded. So this is using conventional matplotlib scatter plot, and the color is the saturation at these points. And we see that the colors in the points in the yellow circles very nicely matches the information or the information from the ERT. So this is now jointly inverted together. And if I would mess this up, if this was 50% saturation at 10 centimeters depth and 20% saturation at 50 centimeters depth, and if I would change this, then this would, of course, physically not be reasonable, but just for demonstration, I would get a much the data fit would be worse. I would have lower saturation close to the surface, or nothing physically reasonable. So this point information is really accounted for in my joint inversion here. So you can use petrophysical measurements in geophysical inversion if you formulate the geophysical inversion in terms of petrophysics. And this is something that can be realized with PyGIMLi. And with that, I would like to hand over to Thomas.
Yeah, thanks again, Florian. I'm taking over for the last 10 or 15 minutes. I'm going to show my screen again. I guess you can see it. What I did in the meanwhile was not much. I just stored, like we did for the XY, for the X1 result, I just stored the result, the mesh, and also the resistivity in the model. And actually, we have two perpendicular profiles that we would like to visualize together. So we have a 3D problem. So let's first look at 3D visualization of 2D problems. So those are 2D meshes. So what we have to do is to bring them into 3 dimensions. So what I'm doing is I'm first setting the dimension to 3, which is just a simple call, set dimension 3. But then I'm still having x and set value. So what I have to do for the result, what I have to do with the result is to switch the coordinate. Switch coordinates 1 and 2 means switching the y into z coordinate, right? And then I'm still having to translate it to the correct position. Yes, every mesh has nice functions for translating, rotating, scaling, and everything. So what I'm doing here is just to shift it to the 0.6 meters that we doesn't gonna need it, and then we just show the result, which is now a 3D mesh, and it should be 3D visualization. And I'm getting in a so-called switch coordinate. It's called swap coordinates. And if I'm doing so, I'm having a 3D mesh, having my 2D profile. And of course, I can also use the same directions that I used before. Just 1 moment, I'm calling this again. I'm using the same color bar options, the same color scale and everything. And this is now I have my mesh into X and Z direction. Okay, I also want to do this for the other profile, which is a profile in the right direction. So what I first have to do is to swap my X into Z coordinates for the X1 result. Then I'm again doing the same stuff after setting the dimension to 3. I'm switching the X with a Y coordinate because this profile runs into the Y axis. So this is turning into the Y axis, and then I'm translating it into the correct position, which in this case was 1, 0, 1. So the first profile we extracted at X equals 1, and then I'm gonna show the X1 result with the same keyword arguments, and then we see it here. Of course, we would like to visualize it together, and then I'm just using the same argument. So PG show X1 result with the keyword arguments, and I'm saying and I'm just saying, well, hold for a moment, I want to plot something else. So hold true, and then I'm using the PyVista plotting, and I'm drawing another mesh on the same plot, which is the return argument of the PG show. So I'm using the same plotting, just like all draw polling routines in PyGIMLi, and I now want to visualize the Y result. For this reason, I have to specify label resistivity, keyword arguments, and if I do so, I still have to finally say, no, don't hold it anymore, show it. And then I see the result, which I probably switch from the right-hand side mode to the arrow mode. And I have both results at the same time, so I can scroll in. I having the regular mesh and the irregular mesh visualized together, so I can also bring 2D into 3D. But what I'm actually interested in is to do 3D inversion. So again, I have to create a 3D mesh, and I have to use a 3D manager. So again, we do the same thing. So it's called mesh tools. And if you look at mesh tools, great. There's a paramesh PLC 3D. So again, now we're using the full data set, the full 3D data set, and we're putting it in. And for this reason, we are just using the default option and calling the same thing PLC, and I'm going to show the PLC, and I'm having a subsurface image which is showing the geometry of a subsurface. So what I actually want to show is a mesh created from the PLC. So again, there's a function create mesh, the same function, which is taking the PLC, but now we go into a different mesh generator. We're now using TEPGen as a heterohedral mesh generator, and for this, the quality definition is a circum radius to length error. So that's a totally different structure. I can look at the I can try to look at a mesh with wireframe. Maybe you know it from PowerView, but you can do most of the stuff also inside. And if you look closer here, then sorry. Yeah, I messed it up somehow. I did not zoom into the plot. If you look closer here, we have fine discretization where the electrodes are and a microcausal discretization in the outside, which is just what we did last time on the 2D inversion. So now we have it. And again, we create a manager, ERT manager. Now we're using the full 3D data. Again, set mesh. So it's really the same thing. And again, manager.invert. This time I'm saying verbose equals true to be able to see what's being done. And shouldn't take long. It's still running, okay. Probably this is my log level that I said before. Oh no, now I'm seeing some result. So this is just on a laptop, which is fairly weak. But I can already start on doing the visualization, which is almost like we did before. As we're seeing, the chi-square is starting at 400 and it's going down and hopefully reaching value close to 1. And again, extracting my parameter domain, which is now a 3D model, and I'm letting this result 3D resistivity with a model, and then I'm trying to show some result. And what I'm interested in is the good conductor. So that's why I'm defining a threshold, which is an object passed to PyVista, and I'm like to use a threshold value of 400 ohm meters, working on the resistivity, and I'm interested in the lower one. So this is method lower. Okay, now I'm seeing the inversion has reached the end. It's not a perfect fit, so it's a chi-square 3. This means something about 2.5 to 3% RMS, so still a good value. And then I can look at the result. So I'm looking at the result 3D. I'm using the resistivity as a label, and I'm using the surface, which means all the object of the triangles, and then I'm using a filter, which is the threshold filter. It's a bit bulky interface, but it's not really complicated. So I can really also automate my whole plotting, and then I see all my results here. Of course, the color scale just goes to 400 ohm meters. So what I like to do is, of course, using the same color scale as before. And now we see the the good conductors here. And again, I'd like to also to draw a slice. I will speed it up a little bit to again plot something on an existing plot. And in this case, I'm using a different filter. I'm not using a threshold. I'm using a slice, which is normal to the y direction and perpendicular. Now in the y direction, and I'm just want to show the result along with a good conductor, so that I have a 2D slice and an ISO value. And this is my result that I could eventually use. So I'm having the good conductor and then having the 3D model. And of course, I could also plot the whole 3D model and different slices by the same objects. So this is 3D inversion basically, and of course we can do much more with a 3D inversion. So let's again look at some example data set. So like before we get example data, we use the same function, EAT, you can 2017, and then I'm trying to use different time steps. I'm just starting with one time step 0, and I'm trying to color code and code my numbers with an integer value with 03 with 3 digits. My number dot that right. Of course, this needs to be an F string, which is a really nice opportunity. So I have it here. I have my data, and I would just extract the subset from it like we did before. Like equals 1.4, for instance, and then I'm again setting the sensors just for playing the x values 1 and the y value with 0, and z value with 0, so that we end up with a y value only. And once we have done this, then we can just create a loop around it, and I'm just making a loop, and I just selected some time step, which is 1, 2, 4, 10, 40, just a few time steps, and doing this again, and I'm collecting all the data in a list, and then just appending this data to the inner list, and then I have my data object, which is now several data sets with the same content. And what I'm doing is really easy, is using a dedicated class which is called time-lapse ERT, and I'm feeding it with the data. And I'm showing it, and I'm having 14 electrodes, 129 data, 6 time steps. So what I can do now is a lot of stuff like filtering, masking out data, error estimation on the time-lapse level or whatever, but I won't go into detail on this one. What I want to do is inversion. So there's a standard inversion, and there's an example which is explaining with all the options that you could use to do the to use different time-lapse strategies like reference model inversion, difference inversion, and whatever. So what I'm just trying to use is, for instance, a parameter depth of 1.3 meters, and for instance, a correlation length to a statistical model, which is using 1 meter in the x direction and 1.3 meters in the y direction. And what I'm then doing is calling the inversion, and it's running. It's already running. So I try to show all models, and this is presenting all my models. I could squeeze it a little bit, get rid of the get rid of the color bars. I'll put the color bars vertical, so I have my color bar orientation. Vertical color bars, so I have it a bit more compact. So I see my 6 different models, but usually I'm more interested in the changes of a model, and that's why there's a special option in it, which is displaying the ratio instead of the a resistivity. And I see the baseline, which is the first time step, the time step 0, and then I'm seeing for all the other measurements, I see the changes, which is the ratio between the time step resistivity divided by the baseline resistivity. So there's not much water here at the beginning, but we see the water from the infiltration that's taking place here is going to take place. And of course, we can do the same thing also in a so-called 4D inversion. In this case, I'm just using the same manager. So inside there's a manager which is using the same constraints. So now I'm using this multi-frame inversion model. So inverting all data at once and constraining the models along each other along the time axis. And if I'm doing so and calling again the show all models function, then I have the normal models again using ratio 2, and I could also set up the color map a little bit like I'm imagining a factor of 2 for the increase and for the decrease, and now I'm getting a completely different model. And I would forward you to the example shown on the PyGIMLi website, which is really demonstrating that you might end up with a lot of artifacts if you're using sequential inversion, and you rather get rid of the artifacts and having much more compact models, because the whole temporal constraining is really stabilizing the whole inversion process. And this is pretty much what I wanted to say about time-lapse inversion. And at this point, I guess we might have some time for questions.
Excellent. Thank you very much for a very detailed presentation. So you have one person with a hand raised. If we want to, let's see.
They can unmute themselves and ask their question. Oh, I guess they put their hand down.
I guess so.
Mm-hmm.
All right. Let's say if anyone has any last minute questions, feel free to raise your hand so we can unmute your mic or throw into the Q&A function or into the chat. Give a quick few seconds just to see if any last minute questions come in.
Yeah, not if you, I'm pretty sure you have questions. There have been a lot of questions in the chat. So whenever you have questions, go to the GitHub repository, go to the MetaMarks flag and get in contact with us and contribute to PyGIMLi, which is, we hope to demonstrate more than just a software package, which is really helping you to achieve your research goals far beyond ERT. Today we focus on ERT, but we can also use the same strategies for any inversion and for different types of coupling. Yes, inversion of SIP is considered yes and no. There's for spectral induced polarization, there's another package which is called PyBird, which is having dedicated classes for both time domain IP and frequency domain IP, where we're also using spectrally constrained inversion. So in this case, it's just like in time-lapse inversion, we are having constraints along the frequency axis and frequency domain IP, and on the time axis, or more recently in the new approach along the dBi axis in the time domain inversion. So I guess this could be a subject of a follow-up.
Absolutely.
Crosshole seismics. Yes. Florian, do you remember? It does, of course, a lot of crosshole seismics and refraction seismics on the web page, but I'm not sure whether we have a 3D inversion result. There's
no, we just have a we just have a modeling example on how to forward simulate refraction measurements in 3D, and we have a 2D crosshole inversion example. But in general, both components are there. You have the inversion thing, and you have the inversion side of things, and you have the 3D modeling side of things. So you could use the inversion manager with a 3D mesh. That should be possible, but we don't have an example on this made ready.
Just because we don't have data right now. So maybe it's up to you to provide data, to provide an example and a nice story, a nice contribution.
So it looks like we have a final question asking if the national organization has interest in having a detailed class on resistivity time-lapse applications with PyGIMLi. Would y'all be able to, would they be able to reach out to y'all to make that happen, or is that a possibility?
Yeah, I don't fully understand what there is a time-lapse ERT class.
Yeah, I think they're asking if they could almost like set up a I guess a more detailed like PyGIMLi based time-lapse ERT class for like, or is like, yeah, I'm not sure if there's
yeah,
I
also understood class in terms more of a course, not a time-lapse ERT class. Yeah, I mean, presentations are definitely possible. I mean, we all have teaching duties ourselves, so depends a bit on the package that that you have in mind, and we also don't know which organization this is, but just approach us via email, and we're happy to discuss. And there's another question on the DOI, which is the depth of investigation. There's not a detailed, not a ready-made function for this, but you can just follow the formulation, and you basically need 2 forward simulations with different starting models, and you have to make sure that the starting model is also the reference model. Otherwise, this does not work. But I have a script to do that. So if you approach us via email, we can also send this or also add this to the website in perspective.
Yeah, so this would be the Oldenburg approach to the DOI. There's also the alternative Auken and Christensen approach, which is based on coverage, on sensitivity. So this is really super easy to implement. We just didn't do it so far.
Excellent. All right, so I think that should just about wrap things up here. I'll say thank you, Thomas, Florian, and Carsten for taking the time to come here and give this presentation on PyGIMLi and to answer all the questions that people had over the course of it. Yeah, it was very interesting, very amazing to kind of see the full depth of or I mean, just doesn't even to really scratch the surface of the things that PyGIMLi can do. So thank you very much for taking the time for all that. Thank you everyone for joining us. The recording from today's webinar will be posted on the SEG YouTube channel in the open source software playlist after some time, once the recording itself is finalized and edited. Yeah, keep your eyes out for more SEG student subcommittee webinars. As you might have heard mentioned a couple times, there is going to be talk and interest and a lot of material that could go into a second PyGIMLi webinar, and so also we'll see what availability and timing can work like. But it'd be great to have y'all back to go even further in depth into more of its applications. So everyone can keep an eye out for that. Please keep an eye out on our social media for any future webinars for this or for anything else. And I'd like to thank you all again for putting together this amazing presentation.
Thanks for inviting us. It was a pleasure for us.
Absolutely.
Yeah, I can only second that. Thank you very much for the invitation.
Yeah,
And
thank
for
you.
organizing the whole series, not only today. We also followed the other presentations, and that's really great initiative.
Thank you.
Okay.
All right.
Bye-bye.
Bye-bye.
Thank you all.